Now we are going to talk about two internal combustion engines. So, one of that internal combustion engine is called gasoline engine, which was proposed by Nikolaus Otto around 1876. So, long after of course, Stirling engine. Internal combustion engines means wherever the heat is produced inside the engine. External combustion engine, that combustion happens to get the heat. So, here we are not having any combustion, but we are giving the heat from outside. So, if the engine is designed such a way that the heat is getting generated inside the engine, then we call that as internal combustion engine, and gasoline engine is one of the internal combustion engine. So, it has this typical 4 steps again. However, there is also a 5th step or the first step, where the engine takes away the fuel gas combination. Both fuel and gas it takes in the first step. Initially there is nothing inside the engine. So, because the volume is 0, as you can see, the first step is called intake step. It goes to 1, meaning it takes away the gas inside the engine, followed by an adiabatic compression. Now, you know that in adiabatic compression what happens, the temperature increases. So, in 1 to 2 the temperature suddenly increases from 1 to 2, and then this 2 to 3 is called a combustion step, where the fuel that is there, because of the high temperature the fuel gets burned. Suddenly volume does not change, but the burning of the fuel generates lot of heat, and that heat will now help to move the piston in an adiabatic manner from 3 to 4, and that is called power stroke. This is what actually drives the piston and drives everything, and then that followed by a cooling step from 4 to 1, where heat will go outside, and then the fuel 1 to 5 the fuel will be ejected out of the or fuel gas combination will be ejected out. It is called exhaust. This is the exhaust step. In one step also, the pressure in this 4 to 1 the pressure decreases, where some of the gas is released until the pressure comes to 1 atmospheric pressure. Otherwise, at 4 pressure is higher than the atmospheric pressure. Then at 1 it becomes atmospheric pressure. So, P0 is the atmospheric pressure. Now, in this particular step we are going to calculate again the efficiency of this particular engine. So, you can see that in 1 to 2 step it is an adiabatic compression process. Okay, we can talk about 5 to 1 step, which is nothing but if you talk about an ideal gas. So, PV equal to NKT or nRT. So, in that volume is 0. So, at constant atmospheric pressure gas is just taken in. So, N goes from 0 to some value, that is it. Now, main thing is the 1 to 2, which is the compression process, in which your Q equal to 0. So, no heat is ejected or taken in. So, therefore, we do not have to worry about that. In 2 to 3 you know that the Q, that is Q in, or you can say QH as it is given here, is again CV T3 minus T2. 3 to 4 Q equal to 0 again, and 4 to 1 QL, which is CV T1 to T4. Now, you see I have not done the work done and all, because we know that for any cyclic process the U is going to be 0. If U is going to be 0, then we know that Q equal to minus W. So, total work done by the system is nothing but the negative of the total heat, or total work done by the system is just the heat. So, we know for a cyclic process your U equals to 0. So, therefore, total work done by the system is nothing but total heat. So, now if I calculate the efficiency of the engine, it will be total work done by the system, which is Q tot, which is QH plus QL, and the input heat is just QH. So, that is the efficiency of the engine, which again gives us QL by QH. Now, this is always the case, right? Every engine we see that it is 1 plus QL by QH, except the way it is, if it is done the way that in 2 steps only you take in the heat and throw out the heat, but if you take in the heat in multiple steps, of course, it will not be the case. Now, here there are 2 adiabatic steps. So, no heat is taken in and out. So, it turns out that we can write that as 1 plus QL by QH. Now, what will be the value of that? So, eta is 1 plus QL by QH, and we know that QL is CV. Let us go back and see what is the QL. CV T1 minus T4, and QH is CV T3 minus T2. So, 1 plus T1 minus T4 by T3 minus T2. Now, in order to simplify this process, we have to get some relations from this. So, let me draw it again just for remembering. Now, you see that this 1 to 2 is an adiabatic process. So, we can use the formula for an adiabatic process, which is T1 V1 to the power gamma minus 1 is T2 V2 to the power gamma minus 1. For 3 to 4 also we can do the same thing, T4 V4 to the power gamma minus 1 is T3 V3 to the power gamma minus 1. Now, once we take the ratio of that, we will get T1 by T4 is equal to T2 by T3, because V1 equal to V4 and V2 equal to V3. Okay. So, now once we get that, we know that I can put minus 1 on both sides, you can get T1 minus T4 by T4, T2 minus T3 by T3. Okay. So, now I can go 1 minus T1 minus T4, I can take the numerator on this side to down, T2 minus T3 is equal to T4 minus T3. But I have T1 minus T4 and T3 minus T2. So, I need a minus sign. So, this one becomes 1 minus T4 by T3. Also, we know from this relation is that T1 by T4 is equal to T2 by T3, and if I rearrange that, I will get T1 by T2 is equal to T4 by T3. So, you can also write as 1 minus T1 by T2. So, you see now the efficiency of this particular engine depends on the difference in temperature between 1 and 2. That is the difference of a compression. So, during the compression how much difference of temperature you can make, that will determine the efficiency of the engine. So, typically at 1 it is at normal temperature 300 Kelvin, and in 2 by compression it goes approximately 500. So, if you take that, then you can calculate the efficiency to be 1 minus let us say 300 by 500. So, 1 minus 3 by 5, so 0.4. Okay. So, basically depending on 500, 600 whatever. So, you get ideal efficiency as 0.4, 0.5, however, the actual efficiency goes to 0.35 because of losses in many other things. So, depending on how much you can compress, that will give rise to the amount of temperature, and that will give rise to efficiency. So, that is the gasoline engine, and little bit later, like 20 years down the line, around 1896, Rudolph Diesel proposed another type of engine called diesel engine, and again we have the diesel cars also which works in that way. So, the difference between gasoline engine and diesel engine is that in diesel engine only air is taken in, not the air fuel mixture. So, again in the first step there is an intake step where the air is taken in, and again it gets compressed to a very large extent, and during this compression process the air gets compressed. So, of course, the temperature goes very, very high, and then in the second to third step the fuel gets injected, and in that high temperature the fuel gets burned. You do not need any spark or anything to burn the fuel, because the temperature is high enough at the stage 2 that the fuel gets burned, and it is injected in such a way that the pressure remains constant between 2 to 3, and once that gets burned, then the next step is the power stroke, where it will push the piston and come from 3 to 4, and then the other two steps like 3 to 4 and 4 to 1 is same like a gasoline engine. So, the only difference is that here it is like a air diesel engine, where only the air is compressed, not the air fuel mixture, that is the only difference. Now, here also you can calculate the efficiency. Let us do that. So, again in the first step 1 to 2 it is an adiabatic step. So, Q is 0, And second to third step is it is a constant pressure process. So, Q is Cp T3 minus T2, this is the QH actually, and 3 to 4 step again Q equal to 0, and 4 to 1 step where the QL is Cv, because it is a constant volume process, T1 minus T4. See, you see here that I am not using any minus sign or anything, because since I am going in a cyclic manner, the signs will automatically come in. For example, if you look at QH, since T3 is higher than T2, QH is a positive quantity. So, a positive heat is, as I told you in the first law discussion time, that a positive heat is heat that goes into the system, because that is going to increase the internal energy of the system. A negative heat automatically means that heat is going out of the system. Now, you see that T1 is less than T4. So, therefore, QL by itself is a negative number, which means the heat is going out of the system. So, now we have these 4 values. So, when you calculate the efficiency eta, it is again the same. The total work done by the system is QH plus QL, as I explained just now, and the heat input is nothing but QH only. So, it will be 1 plus QL by QH. Now, let us calculate the we can write down one more step here, 1 plus Cv T1 minus T4 by Cp T3 minus T2. So, efficiency eta is 1 plus Cv T1 minus T4 Cp T3 minus T2. Now, we know that Cp by Cv is gamma. So, it is 1 by gamma T1 minus T4 and T3 minus T2. Now, let us simplify this process, and I am going to draw it here just for remembering. This is a constant pressure process. So, 1, 2, 3 and 4, these are 2 adiabatic processes, and this is a constant pressure process, this is constant volume process. Just to remember that, this is a handy way to have that. Now, let us write the relation. So, first relation that I will write is between the adiabatic step. So, T1 V1 to the power gamma minus 1 is T2 V2 to the power gamma minus 1. Similarly, T4 V4 to the power gamma minus 1 is T3 V3 to the power gamma minus 1. Take the ratio T1 by T4, and we know that V1 equal to V4, right, because it is a constant volume process. But however, volume of 2 and 3 are not same. So, here we are going to get T2 by T3 V2 by V3 to the power gamma minus 1. Okay. Now, V2 and V3, so there is a volume change between 2 and 3. So, V3 by V2 is typically called expansion ratio RE, because here the expansion is happening, and a ratio between 1 and 2 is called compression ratio. See, these ratios are important in order for the efficiency that you can see in a moment. Now, we have this relation, just we will invert it. So, T4 by T1 is T3 by T2 V3 by V2 to the power gamma minus 1. Now, what is the relation of T3 and T2? Let us understand that. For that, we are going to use the relation between 2 and 3. Now, since it is an ideal gas, we can always write P2 V2 by T2 is equal to P3 V3 by T3. We can do that for any 2 points. Now, you see that the pressure is same between P2 and P3. So, cancels. So, therefore, V3 by V2, the expansion ratio is T3 by T2. Okay. So, now we are going to get T4 by T1 as V3 by V2 into V3 by V2 to the power gamma minus 1. So, since V3 by V2 is expansion ratio, we are going to get RE to the power gamma minus 1. So, therefore, RE to the power gamma. So, we have got that, and so now let us come back to this left hand side. So, it is 1 plus 1 by gamma. Let us take T1 common. So, if I take T1 common, it will become 1 minus T4 by T1 and T1 outside. Let us take T2 common. So, T3 by T2 minus 1 T2. Now, we see that let us take a negative of this numerator. So, 1 minus 1 by gamma T 4 by T 1 minus 1 T 3 by T 2 minus 1 T 1 by T 2. Now, let us just put the values 1 minus 1 by gamma T 4 by T 1 is R e to the power gamma, you can see here R e expansion ratio to the power gamma minus 1, and T 3 by T 2 is simply R e. So, R e minus 1 T 1 by T 2. So, this is the efficiency of a diesel engine, which of course depends on the expansion ratio as I said before, and also on the gamma. No, so one can have a calculation typically expansion ratio as 5, R e typical values of this thing will be 5, gamma typical value will be like say 1.4, and you are going to get an efficiency of around 0.5. Ideal efficiency is also almost like 0.3, 0.4, similar to like gasoline engine, although we know that they are a little bit more efficient than gasoline engine, the diesel engines, right. Okay, so, one important thing to discuss here is that in both the gasoline engine and diesel engine, there is this constant pressure process and constant volume processes. In gasoline engine there are two constant volume processes, and in diesel engine one constant pressure and constant volume processes. Now, in constant pressure or volume processes, the temperature changes all the time, and therefore, in order to make a reversible engine you need to place this system in infinite number of heat reservoirs. Therefore, one it is difficult to compare with a Carnot engine, which says that it has to work Carnot engine works between a fixed 2 temperature reservoirs. In this case it is not possible to do so, although we are getting an efficiency which is related to 2 temperatures, but it cannot be directly compared with the Carnot engine, which says that the efficiency is 1 minus T 1 by T 2, because in that case there is only 2 temperatures T 1 and T 2, but in case of diesel engine there are all temperatures are different 1, 2, 3 and 4 all are different, and so it does not really work between only just 2 temperature reservoirs. However, given that they are all reversible steps, one can have an effective 2 temperature differences to represent the efficiency of this engine if possible. So, but it cannot be directly compared with that. We are going to show that all reversible engines have basically same efficiency. The point is that the diesel engines cannot have that reversibility because of this constant pressure and constant volume steps. So, now we are going to show later that Carnot engine has the highest efficiency for working within the 2 temperature reservoirs, and so that means that all reversible engines have highest efficiency than the irreversible engines, and all reversible engines have the same efficiency basically. So, that is why I was telling that given that diesel engine and gasoline engine can be constructed in a reversible manner, its efficiency will be as good as the Carnot engine, because all reversible engine will have to have the same efficiency. But it practically it is not possible, because a constant temperature difference process cannot be done in a reversible way.